finally, let's take this theory we now have for computing flow, and what I want to do is to apply it to my point source. I want to go here and apply it to this idea that if I have this sphere of radius r, I will call it radius r, and I think about the velocity v of r flowing at that distance r from the center here, I know from conservation of mass that the net flow I'm going to have out of this surface actually has to match exactly the amount of flow that I'm pumping into the source. That's from conservation of mass. But now we have a way of relating the velocity at the surface to the total flow, and this should allow us then to solve for that velocity. So let us then carry out that calculation. Let's think about then the flow at the surface of a sphere of radius r from a point source. Of current I. Okay, so from conservation of mass, we know that the flow in to that sphere, which is coming from our hose, has to equal the flow out of the sphere at the surface. The flow in, we've determined already, was equal to I. That was what we were pumping into our system. And the flow out then is going to be the sum over all of my patches n, if I divide my whole surface into a whole series of patches, and around each patch there's a certain amount of current flowing out of it. And those patches, when I add them up, each patch we've just determined has an amount of flow equal to rho naught times the velocity at the location of that particular patch, dotted with the area vector for that patch. So we're taking this surface of this sphere and we're dividing it into many, many tiny patches across the sphere, and we're simply adding up the flow across each and every one of those patches until we've covered up the entire sphere. Now this summation we should recognize again clearly as we take the limit of many, many tiny patches and add them up. This is going to become an integral. But because now we are integrating over a surface, a two-dimensional surface, this is going to be a double or a surface integral. The quantity we are integrating is rho naught times the velocity. Each little area patch becomes then dot d area vector. And the final piece of notation to note is that we're integrating across this surface, which is a closed surface, because we have to be sure to account for each and every tiny little bit of flow that might be coming out of this surface. So it's a closed surface integral, which we denote by sketching a little closed surface, superposing it on the integrand. And our job now is to calculate this integral, equate it to I, and then we were going to learn something about the velocity at the surface of our sphere. So, to do this, let's begin to evaluate our surface integral. We're going to see many of these throughout the semester, so I want to take you through this step by step. I think you'll see, though, that the steps are fairly mathematically not too grungy, but maybe just a little tricky the first couple times you see them. So first thing I always do for these integrals is I like to work out the value of the dot product. So this will be rho naught, the magnitude of the velocity that we're talking about, right, times the magnitude of the area vector, times the cosine of the angle between them. Now, when we think about the flow pattern from our little point source in the middle, I think it's pretty clear if we consider any particular patch that the flow is going to be directly outward from that point source. But notice that that outward direction is in fact the same direction as the normal vector to that particular patch. So therefore the angle between the velocity vector and the area patch vector is going to be 0, and the cosine of 0 we know is 1. So the cosine handles very nicely. dA, the magnitude of dA, we can also figure out. That's just the area of each particular patch as I go around the sphere. As for the magnitude of the velocity, we don't know what the velocity is at the surface of our sphere yet. In fact, that's ultimately what we're trying to determine. One thing we do know, though, is that this is the velocity of the flow field at the location of the surface that we're integrating around. So this is the velocity, the magnitude of the velocity at distance r away from the central point source at the center of my sphere. Okay, now the key thing about that velocity is that it is constant, right? It should be equal outward in all directions by symmetry. That then allows me to factor out, to pull out the constants from my integral. Rho naught is constant around my surface, as well as v is constant across the surface, although it depends on the radius of the surface. Those are two constants, unchanging as I go around the surface, so they can be pulled out. So I'm going to have rho naught times v of r. And all that's left inside then is the integral around that closed surface of the area elements, and the cosine had just given us 1. Now, this integral itself just adds up the areas of all of my tiny patches going around the sphere. So this is just going to give me the total area of the sphere, which is 4 pi r squared. And so I have a final result that the total current that I'm pumping in down that hose has to match the total current out of the sphere, and the total current out of that sphere, putting all of these results together, is 4 pi. There's a factor of rho naught that I don't want to forget. It depends on distance squared, and then multiplies v of r, and that gives me all of my factors. So finally, we are able to actually solve for the velocity field from this point source. So the velocity, v of r, is going to be nothing other than I divided by 4 pi rho naught r squared. That gives me the magnitude of the velocity. And if I want to make it into a vector, because velocity does have a direction, the velocity vector will just be this magnitude times the direction of the flow, and we already determined that the direction of the flow is directly outward from the center. And so then this must multiply an outward unit vector, r hat. So let me put then a box around this final result. And the really exciting piece of this, if you've noticed, is that the velocity field indeed is outward and drops like 1 over distance squared, exactly like a point charge. So we have succeeded in constructing this very nice exact analog of a fluid way of representing the a flow, of representing the electric field for any given situation. And that, again, definitely gives us the happy professor symbol. And we'll pick this up next time in the next lecture.